Hello, good morning, everyone.
Good morning, everyone. Today, my topic is still the Apple code up and down. Fuzz Apple code common in kernel and user mode for fun and profit. This is also our topic. This is Juwei.
Hello, everyone. Good morning. This is me. The first line is my Twitter account, and I joined Trend Macro since 2013. I have some experience in Windows kernel, and I am the author of Trend Macro Rootkit and Bootkit clean tool. I am also the major author of Trend Macro ransomware decryption tool. Now I focus on iOS, Android, and macOS vulnerability hunting and exploit. Okay.
I am Li Lang. I have joined Trend Micro since 2016. I was majoring macOS and iOS vulnerability and malware hunting. And now I'm focusing on iOS and Android exploit detection. This is another also our topic. He's Moni Lee, and he's absent by something reason. And she's focused on exploit detection and iOS, macOS, Windows, and Android vulnerability. Today, this is the agenda of our topic about XPC in user mode. We will talk about our fuzzing strategy and study one case. This is the smart fuzz XCON agenda. We will introduce our fuzzing architecture and then talk about the root case study. Now let's talk about the smart fuzzing XPC first. XPC is one of the low-level inter-process communication mechanisms. The main security purpose is to separate the privilege for different components. As we all know, a common technical to break out of sandbox is to obtain the code execution in a higher privilege or unsandbox daemon. And iOS and macOS provide so many of these kinds of system services in order to implement different functions for applications. So that is why we take XPC mechanism and our fuzzing target. XPC has its own data types, such as int, double, and dictionary. However, in the end, all of this data will be serialized into XPC messages and set by match message function. For match messages, there are two kinds of introduced symbol, including symbol and complicated ones. And what is the XPC message looks like in the memory? We got a real message through debugging. From this picture, we can see that the content in the red box is the match message header. The green box content is the count of the message body. Here is the one. Next is the message decryptors, which contain the XPC data object in the XPC messages. Following the magic and the vision value in the yellow box are the XPC dictionary data. This information composed an XPC match message. When one XPC service process a request from other processes, it should deserialize this XPC message by match message mechanism first, and then using XPC mechanism to process this XPC data. Finally, corresponding XPC service will receive the data they accept and complete their tasks. However, we cannot ensure that the data can be processed correctly in all these steps. Actually, many vulnerabilities related to these three steps have been disclosed. And for these vulnerabilities, the main issue is that the mechanism we mentioned above cannot pass and process the malformed message correctly. For example, there are many type confusion vulnerabilities in XPC mechanism. And there are also many vulnerabilities caused by services themselves, which cannot process malformed data. Therefore, the main goal for us to trigger potential bugs is to craft those malformed match messages. Here, contents in the red box are the data we can craft, including body count, message descriptors, and dictionary data. Based on this information, we developed an easy but very efficient fuzzing tool. Our fuzzing strategies are aimed to easy control, easy to mutate, easy to monitor, and easy to reproduce. This is the architecture of our fuzzing tool for XPC. For the mutation engine, we introduced a concept of procedure random algorithm. Using this algorithm, we can get a large number of random numbers, which can help us to compose the fuzzing match messages. And for one seed, we can always get the same pseudo-random number sequence, so it can make the crash reproduce easily. With this malformed match message, we use the match message executor to send this message to target XPC service. And for each target service, we can monitor its status and exit code. If it crashed, we can reproduce the seed and reproduce the crash scenario through the side random number sequence which are generated by this seed. The pseudo number random algorithm we use is based on Mason-Twister algorithm, which has been implemented in NumPy library. Then we will replace some of normal values with our procedure random number in the message body. For one seed, we limit the amount of the random numbers generated to a fixed range, such as 1024 or 2048. Because if we do not limit the amount, it will take a long time to reproduce if the target XPC service crashed. Our fuzzing target are the XPC service. As we all know, XPC service are managed by launchd, so we can use launchctl to dump the details of this XPC service. For each XPC service, we initialized a connection port in order to send the fuzzing match messages. Actually, in order to easily control our fuzzing tool, we wrapped the main interface by Python script, including getting the XPC service connection, event handler, and message send functions. Then we use the Python to implement the whole fuzzing processes from match message correction, constriction, and send them to target XPC service. Due to one XPC service may have many processes, so we crashed. So for crash monitoring, the strategy we use is to monitor the status of the process cursor for each XPC service. If there is any one process exit, we will get its exit code and find whether it is abnormal abort. The finger in the right shows the exit code and its abnormal action. For example, when you go to the Xcode 11, then congratulations, you got an execution band access, and you can try to reproduce it. There are also many methods to reproduce the crash. Here we list 4, including log, crash film, crash dump, and seed mentioned before. We use the seed based on Poseidon random number generator with Mason twister algorithm to fuzz the target. So for each fuzzing circle, we can simply save the seeds in the server, and no need to save any middle status and data. After comparison, you can find that reproduced by seed only costs small storage, and its speed is fast. What's more, is also only spend a little human effort than others. Here is a vulnerability we have found using these tools. libATS server. libATS server is the service which using to process font information. We found that it has not boundary check when using the memory copy in the read function. This is the root cause analysis. In the place A, we could find that V53 is the copy size and equal to A3. And in the place B, we can see that the A3 equal to V6, and backtrace the color in the place C. We found that the V84 is the size value and get from V238. However, in the place of D, we found that the V238 equal to A3, and is the message we send from outside, so we can control the copy size in the remote service client. Next, I will let Juwei to introduce our smart fuzzing XNU.
Okay, hello everyone. This is about how to smart the kernel part XNU. Okay. First, let me introduce what I will introduce today. I will introduce our tool, Pending XNU. Actually, this is a tool of porting Google's syscall to support macOS XNU. As you know, syscall is a great tool to fuzz syscall APIs, right? But it doesn't support fuzzing macOS XNU. So actually, I just port this project to support XNU. And in order to make this tool work well under macOS, we need to modify the XNU project to add some features, for example, the code coverage, to make this tool works well. Okay, finally, I will give you a sample about how to root the macOS. In order to make our tool work, we need to improve 2 parts. The first part is the fuzzer. The second part is the XNU. As for the fuzzer part, I wrote more than 500 API patterns, and I prefer to use Vim Fusion. So I add support for Vim Fusion in Pending XNU tool. And as you know, we must implement a macOS executor to execute these syscall requests. The second part, XNU, in order to, as you know, syscall is a code coverage-driven fuzzing tool. So we must to add code coverage in existing XNU project. And also, we need to enable the default kernel address sanitizer and add the kernel memory sanitizer to make it better. Okay, this is architecture of our tool, and certainly this is almost the same of syscaller. And let me introduce the basic process. Step 1, the VM management on the right side will start the client instance, and the syntax engine in the client instance will note the API patterns and the corpus DB, and then it will generate the programs and also pass the programs to the mutation engine to mutate the programs. Then these programs will be consumed by the syscall executor. The syscall executor will check the return value to check maybe if there is something like heap memory leak. And it also will get the code coverage. It will update the corpus DB. And this is almost the same with Google syscaller, but the modules marked in green is the key modules or our efforts on this module. Okay, I will highlight these modules later. This is an example of the API patterns. I wrote about 530 API patterns in our tool in such kind TXT files. And another picture, the right picture describes the code coverage enabled in the XNU kernel. I instrument the sanitizer cover trace PC stop function in almost every basic blocks. Okay, so this is my efforts. I developed the API patterns, and I enable the kernel address sanitizer. As you may know, the kernel, if you enable the default kernel address sanitizer without any modification, at least under my experiments, you can't start the kernel. And I also developed the code coverage sanitizer and the kernel memory sanitizer. Okay, let's see the first part, the syntax engine and the corpus. I reused this part from syscaller, so I didn't modify anything. Just a quick glance. Firstly, you need to write the TXT files, the API patterns in TXT, and call the sysextract and sysgen to generate the Go files based on the API patterns. And then the generation engine will generate the programs. Also, the mutation engine will mutate the programs. Then these programs will be delivered to the executor. The executor will execute these requests to fuzz the underlying kernel module, XNU. As for how to write these API patterns, you can refer to syscaller's descriptions syntax, and also you can refer to the sample text in the project, in syscaller project. And the second part is about the sanitizers. Let's have a look at the kernel mode sanitizers. I list the top 3 sanitizers used in my tool. The first one is the kernel sanitizer coverage. This is the most important one. It is used to get the function level, block level, or edge level code coverage. You can use the LLVM to instrument the stop functions into every basic blocks, but there's no existing callback or the stop functions in XNU project. You must implement the callback function by yourself. The second one is kernel address sanitizer. It is used to detect OB, access, use out free, double free, and so on. XNU has the default module. You can enable it, but it is not easy to enable it. The second one, the last one is kernel memory sanitizer. There's no current module in XNU, so you must add this module by yourself. This module is used to detect the uninitialized memory. Okay, the first module, the code coverage, we need to develop a new module to support this. See this picture. As for me, I add some fields in the kernel task structure. At the end of this structure, I add some fields such as cover mode, cover size. If you know the Linux kcover module, you may be very familiar with these fields. And I also implement the function sanitizer cover trace PC. Okay, let's see this picture. After everything done, you can get the kernel with code coverage enabled. You can see this sanitizer cover trace PC is already instrumented in every block. Okay, the kernel address sanitizer. KDK now provides this kernel KSON module, and it works well. But if you want to compare it by yourself, at least for me, I can't compare it successfully without any modification. And next, I will introduce the KSON. It consists of God pages, shadow memory, and operations. It can protect globs, stack, and heap memory. Let's see how KSON protects this kind of memory. If you call the string L copy in kernel in XNU, it calls ASON string L copy if you enable the KSON feature. And ASON string L copy will internally check the shadow memory to check if it is legal. If not, it will panic the kernel to notify the users. Then you can get something wrong, maybe UEF vulnerability. Let's see the shadow memory. When you call some operation to allocate the kernel memory, the KSON will allocate additional red zone, the left, the right red zone, and the related shadow memory. And it will, let's see the operations. I list part of them. The heap memory operations, the stack memory operation, and the other memory operations. Let's see an example about how to detect UEF by using KSON. When you allocate a buffer in kernel memory, the related shadow memory is initialized as value 0. And when this memory is freed, the shadow memory value becomes negative value, for example, FF, FD, FE, something like that. And when used after free, you use the freed buffer, the related operation like string copy or memory move or something like that will internally check the shadow memory if it is legal. The FF is illegal, so it will panic the kernel to let you know there's something wrong. Okay, the last one, the kernel memory sanitizer. This is very simple. It is used to detect the uninitialized memory. We just what we need to do is to initialize all the uninitialized memory. So see an example. The k-alloc block, you just need to add the member set at the end of this function. As for me, I member set all the new allocate heap memory to value DE byte. So let's see an example. This is a real case vulnerability. And what I did is, besides the KMSON, kernel memory sanitizer, I also add a new syscall, panic or report. So in my fuzzer user mode application, the fuzzer, it detects the continuous 3 bytes DE, and it will call my syscall panic report to let my fuzzer know there's a potential heap leak. So you can see I wrote this panic log. It's very small, and you can see that I wrote the syscall ID here, so you can get which syscall has the potential heap memory leak. Okay, and this is the buffer, the 3D buffer bytes. Okay, so the conclusion is that if you want to make your fuzzer smart, you need to use the syntax engine to know the API patterns and use the sanitizers to help detect some vulnerabilities. Okay, let's see the macOS root case. Months ago, I developed the Pending XNU version 1 with 500 API patterns and the code coverage support in XNU. And then I started, I get lots of the crazy crashes in the Apple XNU. The accurate number, the unique crash number is 54. Most of them are of type non-point dereference and assert failure. As you know, Apple doesn't recognize this kind of bugs as vulnerabilities. So I did but I still get some very qualified vulnerabilities, like the 4413 and the 4425. I combine these two vulnerabilities to root the macOS before 10.14. Okay, let's see these two cases. The first one is the 4413. This case is used to leak the some uninitialized heap memory. For example, it can be used to leak the kernel IPC port object, and it is fixed in macOS 10.14.1 and iOS 12.1. The second vulnerability is NECP type confusion vulnerability. It can be used to write or free arbitrary kernel address. It is fixed in macOS 10.14.1. Okay, let's see the first vulnerability, 4413. You can see this code here at location 1. The p-args length is usually around size 0x300 here. So in my POC, I set the arg size to 0x200 so that this instruction will be skipped and the arg size will not be run paged. And next, the KM alloc will allocate a kernel buffer copy start with size a page, run page, arg size a page. And then it will copy the args information, process arguments information to temp buffer. Later, the temp buffer, the 0x200 size temp buffer will be copied back to the new allocated buffer. And then last, finally, the 0x200 bytes will be copied back to the user mode buffer. But where does the kernel data be copied out? The data actually points the very last 0x200 bytes. Okay, let's see this picture. I think this is very clear. This vulnerability is very simple, and I still don't know why. And you can see this picture. This function will get the process args information at offset 0 of the new allocated page, but it will return the very last 0x200 bytes back to the user mode application. So it's very strange. I don't know why. Let's see how to exploit this case. It's simple. You just need to use the mark message with the OL ports descriptor. This will allocate a buffer in kernel mode and fill the IPC port address in the buffer. Then you can destroy the port's memory by calling mark port destroy. Then finally, you can trick the vulnerability to leak all these IPC port kernel addresses. You can get the address in the user mode. So you can get you can leak the IPC port kernel address now. Okay, let's see how Apple fixes this vulnerability. Very simple. Just add calling b0 after allocate the kernel memory, the page kernel memory. Okay, let's jump to the second vulnerability. This is a vulnerability of type confusion. This vulnerability exists in NECP module in XNU. Let's see the attack surface 1. You can call NECP open and NECP client action APIs to do something. And NECP open will return a handle to the kernel NECP FD data. And then you can use the return handle to NECP client action to call sub client actions here. Okay, let's see the NECP open. It will allocate a kernel object NECP FD data. The structures is as follows. And it will store the buffer in FG data in FP. Then it will return the handle back to the user mode. The user mode application can then call the NECP client action with the provided handle. At location A, it will cause NECP find the FD data according to the user provided handle to find the real kernel object, the NECP FD data. Okay, let's see how it finds this kernel object according to the provided handle. It calls the NECP find FD data. Internally, it calls FP lookup. Use the handle to find the kernel object FP. Then it will verify if the FP is the NECP FD data. Let's see how it verifies. It just verifies if the FO type of the found object equals with the type net policy. Okay. If yes, it will return the object as NECP FD data. So let's have a summary here. See the normal process. You firstly call NECP open. NECP open will create the kernel NECP FD data and stores it in the FP structure and return the corresponding handle to user mode program fuzzer. And then you can call the NECP client action with returned handle to call the sub client actions. And this function will find the NECP FD data according to your given handle. The algorithm is very simple. It just check if the type is the type net policy. If yes, it will call the following sub-client functions. Let's see another attack surface. It's very similar to the first one, just with a different name, the NECP session open and the NECP session action. Very similar to the previous one. The NECP session open will create the kernel object NECP session and return the handle to the user mode fuzzer. And then you can call the NECP session action to call the following actions according to the return handle. So let's let's see the NECP session open function. It creates the NECP session object in kernel and store the new allocated kernel object to FG data in FP and then return the handle back to the user mode fuzzer. Let's see NECP session action. With the given handle, it will get the corresponding NECP session object. Let's see how it gets this object by your handle. Oh, it's almost the same with the previous function, previous one. It also calls fp lookup to get the fp, the kernel object, by your handle, and then it verifies if the FO typer is the typenet policy, right? If yes, it will recognize the found object as ACP session. Okay. So let's see the normal process. You call ACP session open to create the ACP session object in kernel and return the handle back to the user mode further, and then you call ACP session action to find the kernel ACP session object by the handle, return handle. Internally, it checks if the type is a dtypenet policy. If yes, it goes on. So let's have a conclusion. Let's have a summary here. What we have learned so far. In attack surface 1, it creates a kernel object ACP FD data, and then it will return the handle back to your fuzzer. You can use the handle to call ACP client action. The ACP client action will check if the type kernel object type is dtypenet policy. If yes, it will treat this object as ACP FD data. Yes. In attack surface 2, ACP session open and ACP session action are almost the same algorithm. If your handle points to a kernel object of type dtypenet policy, it will recognize the kernel object as ACP session. So you got this vulnerability because ACP FD data is totally different from ACP session object. Okay, surprise. Let's talk about how to exploit this vulnerability. There are two methods. The first one is you can create ACP FD data kernel object by calling ACP open and then call the ACP session action instead of ACP client action to operate on it. The second method is on opposite. You can create ACP session object and call the ACP client action instead of ACP session action to operate on it. So I use the first one. Okay, let's see how I exploit. Step 1, call ACP open to create the underlying ACP FD data object. Pay attention to the structure. At offset 20 and 28 is an update list field in the ACP FD data structure. The ACP open function will initialize this structure, and the value at offset 20 is 0 after initialization, and the 28 is actually a kernel address, points to the update list itself. So let's have a stage update stage status. You call ACP open, and it internally will allocate a kernel object buffer, and at offset 20 and 28, you'll get value 0 and a kernel address. Okay, step 2, call ACP session action on this object. You can see at location B, yes, if the proc locked is false, the session proc UUID and the proc PID will be updated. Let's see this ACP session structure. At offset 20, this value actually is always 0. And you can remember the previous picture. It is always 0 here. And since it is 0, it is false, the proc UUID and proc PID will be updated. The value is the macOS file UUID. So let's have the update here. Step 2, you call ACB session action based on this buffer. Then you get the buffer updated like this. 20, also the 0. And 21 to 28, the 16 bytes is set to macro file UUID, which is controllable by yourself. Okay. The last step, step 3, you can call ACB client action with the client action number 15. Actually, the ACB client copy client update. In this function, finally, it will free address client update. And client update is the first element of the update list. What does it mean? Let's see this one. The client update is the first element here. So the free function actually free kernel address, which stores in starts at the offset 20. So since we can control this UUID, so we can set the macro UUID, the 16 bytes as A, and here we get the we can use this vulnerability to free address 4141414141 with first byte 0. But it doesn't matter because most of the kernel objects are aligned with 16. So the first byte 0 doesn't matter. We can control 7 bytes of 8 is enough. So what we get? We get vulnerability, and we can free an arbitrary kernel address. We can control 7 bytes of this, the high 7 bytes of this kernel address. Let's see how Apple fix it. It's simple. Apple just add a subtype check. In ACB session action, it adds a subcheck if the subtype is 0, and in ACB client action, it adds the subcheck if the subtype is 2. So everything solved. Let's see a demo. I just introduced the 2 vulnerabilities here and the exploits of these 2 vulnerabilities. As for the root, the combined root, you can refer to Ian-Bill's macro portal POC. You can just replace his 2 vulnerabilities with mine. And let's see the demo. 1 minute demo. Sorry. Okay. Start. Okay. This is my POC, and firstly, activate this POC try root, and you can see this is macOS with kernel 17.7.0, and now we are the common user panic or 1. After then we continue activate the POC. I add a lot of the snip here. It is not a must. I just want this POC to run slowly to check if anything wrong. I add a lot of the snip here. Okay, you can already see a lot of the kernel address here. Okay. Press any key to, okay, already done. You can get the root here. The process now is with privileged root. Okay. Done for my demo. Let's continue. Okay. And almost done for my sharing. And this is a future plan of our tour. I need to support, in the future, I may add support for the kernel extension, I mean the L control, the driver, and the L kit. I will add coverage for L kit. You may know L kit is a closed source binary, and I still have plans to add the code coverage for it. Okay, you can see this picture. It is a closed source L kit binary, the Apple HDA module. It is closed source, and I already successfully instrument the code coverage stub functions in this binary in every basic blocks. Okay, since time is limited, if you want to know more message from me for the later build, the Panic XNU, or even our sister projects, Panic Browser, Panic Android, and Panic other things, you can follow my Twitter. And also, you can reply my latest tweet to ask questions about my today's sharing. Okay. Okay, acknowledgement. Certainly, I'm just do a job about port the Google syscall. So, thanks the great project syscall, and thanks EMBU's exploit tactic. Okay, any questions? Thanks. Okay, if you have any questions later, you can contact me via the Twitter. Okay.
I would like to know just about the time you spent developing the fuzzer, and how much time do you spend to find bugs that you show us?
Okay, thank you. The question is how much time I spend to develop the Panic XNU tool, and how much time I found the lots of crashes by running the tool, right? Okay, the first question. How much time I used to develop the Panic XNU? Totally about maybe 2 months. 2 months. Yes, the major efforts I spent is focus on the XNU modification and something on the fuzzer. And how much time I found these vulnerabilities? Actually, most of them, maybe 80% of them, are found within 2 weeks. And today, still, I can receive some vulnerabilities found by this tool. I sent the email to my iPhone once it found a vulnerability. So yesterday, I received a new vulnerability. So it is automation project. Okay, have I answered your question? Okay. Okay, thank you. There's no time more, so you can ask my questions on my tweet. Okay, thank you.